Yeah, so my name's Kevin Warner. I lead an awesome group of automation and development engineers at Waikato Milking Systems. They actually make me look really good. I'm actually pretty useless myself. What we're sort of thinking when Callaghan invited us to come talk to us, to you guys today, we're sort of thinking, how do we show our product, how automation actually improves milking efficiency? And so when we were thinking about that, we thought one of the products we've recently developed is our sheep and goat rotary milking solution. And the reason we wanted to show this one in particular is because it's quite a new product. It actually really clearly takes advantage of automation, whereas some of our more traditional stuff is basically automation's been bolted onto it afterwards. Our sheep and goat version is basically from the beginning, ground up, has been designed with automation in mind. So when we started the development of the sheep and goat product for us, it's quite recent. We had a previous version which was much more basic, very simple solution. When we started this new project, we were lucky we had three really good important things for any good project, I think, to work. One, we had the design itself was driven 100% by farmer feedback. It wasn't the ideas of our engineers on how to make something work. It was actually go to farm, find out what doesn't work, and try and build from there. And the second thing we did is our engineers were actually the ones that went and grabbed that feedback. It wasn't market research teams or sales teams, because sales guys are pretty average most of the time. It was actually the engineers. They had to go and do milkings. They had to go and see how the people used the stuff. And again, we're very lucky. I think it's one of the great things with New Zealand farmers in particular. The guys that helped us, they had no benefit from us. They were just doing it because they wanted to improve milking for dairy goats in this case. So completely selfless, and I think it was really happy that they helped us a lot. And the final thing we had, which was probably the biggest thing, and I hate to say this from an R&D point of view, but we actually sold our first machine way before we designed anything. So now, it's pretty scary when you say it, and especially to R&D guys, it's like the worst thing you can do. But the biggest thing that I think it always works every time is, one, is it absolutely focuses you. And the second thing it does really, really well is it sets a budget. So one, you have a deadline, you have an absolute focus to achieve something, and you have a budget to do it, which are really important things from a development side of things. So the customer that we actually had is actually a crazy guy out of Canada, an awesome guy, really, really knew his stuff. He'd been in dairy goats for a long time, and he'd been around the world and seen all the other machines, and he knew exactly what it wanted. So the thing he wanted to do is he came to us and said, can you comfortably milk and calmly and repeatedly milk 1,000+ goats an hour? Which seems like a pretty big number. And if you think about it, in our case, it's 100 milking units in a rotary. But to milk, it's actually 1,200 goats that we can achieve quite comfortably on it. It means we have to have a goat come on the platform every 2 seconds. A milker has to physically attach something to the goat to milk it every 2 seconds, and the goat has to get off the platform every 2 seconds. So it's a heck of a lot of work. And to do it once is easy enough, and to do it in one rotation is fairly straightforward. But to do it for hour after hour, that's where automation absolutely comes into its own. So what we started with, obviously we have a very big rotary, in this case, like I said, a 100-bale machine. And then we basically added some clever sensor technology to it. That's where the automation comes in. So we need to know exactly where the rotary was at all times. So we have a sensor that basically tells us the exact angle of rotation for the rotary. It's down to 1 millimeter distance, and if you imagine over a 12 or 13 meter radius, that's quite a precise reading. And we also had to basically identify the animals very exact. And the reason we need to do this is because we actually feed the animals an incentive to come on the platform based on production. And then we can also sort the animals from the platform. So I don't know if any of you know anything about goats, but they're incredibly clever animals, and they pretty much can fool you no matter what you try to do with automation. So by sorting them from the platform, again, we improve efficiency because we do a job that a person would otherwise have to do, and it's very difficult to do manually. So that was basically where we got to with the development side of things. And the third thing that we ended up developing, which I'll show you in a video in a second, is an arm that basically automatically presents the cluster to the milker. And this is where we get the efficiency. This is where we have the speed. It's basically, we basically bring the arm up in a similar way to what a robotic milking machine would do. Brings it to where the milker just physically has to grab it, engage it, and attach to the animal. And then it automatically comes off at the end of milking. So I'll show you quickly the video. So that's the arm, basically. The position system tells the arm where it is in rotation. as the animals milk on, they basically walk, and all the milker basically does is grab it, attach it to the animal, and that's basically how we get all the efficiency. It decides, at the moment you see this is from the very early milkings when we first started. We have other cool things on there. We have all the milking results are recorded with milk meters. That data is sent back to a central database. From that we feed to production. We can make decisions based on what that animal's actually doing. We can see health issues that are happening. So again, it's just a lot of technology come together. Database systems are amazing. By collecting that data, you can make some very good decisions. And the other thing we do, basically from a mechanical thing, because not always is automation with electronics and software. Sometimes the best automation is completely mechanical. So in this case, we have a system where the goats come in. They have a lock that actually locks their head in place so they can't move out. Because the other thing with goats is they like to, they're very inquisitive. They like to eat everything in sight. They like to move around. So basically, this is actually when they very first started. So people actually, in this case, have to push them on until they get used to it. They basically get a feed incentive. So they basically put their head down into the bin. That locks them in place. And then there's a mechanical system elsewhere that basically takes it off. And the reason we want to go mechanical is actually, to be honest, electronics do fail. Wires get broken, bits and pieces like that. Mechanical things, they can be set so that they cannot fail. They have to operate. If they don't operate, other things won't operate. So you don't break stuff accidentally. So yeah, that's what we get to, is basically a combination of automation, electronics and software where it needs to be, mechanical where it's also useful. So that's our level. Cool. Thank you very much.
So I'm Steve Harcourt. I head the product development team within LIC Automation, which is a subsidiary of LIC. LIC is a farmer-owned co-op, for those that don't know. So about 20 years ago, really, or just shy of 20 years ago, we started a bit of a journey into automation technology. It was hotly debated at the time. We were a successful herd improvement co-op with information technology solutions and genetics. And the question was asked rightly, why do we want to jump into this very competitive, very challenging technology space? And the answer is really quite simple. We have a lot of staff on the road around the country working day to day with farmers, whether it's technicians doing herd testing or sales staff. And it was becoming increasingly evident that farmers were confronting the very challenging job of farming in an increasingly difficult environment from a regulatory perspective, but also just growth and scale and intensity of farming. And that was putting these challenges on them. And so it was a very staff sort of up initiative to try and build an automation platform to make farming easier, more productive, more profitable. It wasn't entirely altruistic. What was happening was, as farming got harder, as the farms got bigger, customers were starting to lose sight of some of the virtues of our own products, starting to sort of move away from some of the really well-established principles of dairy farming and productivity and profitability. And we really wanted to get them back to that conversation and not just completely sunk by the jobs on farm. So our initiative at the time started very simply, but it was to try and work our way through addressing these sort of challenges to bring farmers back to the real important stuff, which is better decision making and profitability ultimately. I'll walk you through some of the technologies just to show you how they relate to those goals. So pasture measurement and body condition score measurement, everybody understands the value proposition in doing that, but they're both very time-consuming jobs. Our sort of realisation was that farmers in New Zealand aren't doing this as consistently or even as effectively as they should be in terms of what it can deliver to their business. So we have an automated solution for measuring pasture via satellite technology. We have an automated system that we developed with D. Laval to measure body condition score of animals, producing that data on a platter when farmers need it. So great step forward, saves a huge amount of time on farm. Mating is, in New Zealand, a very seasonal job. Huge spike in workload over 6 or 8 weeks of the season. Turmoil on most farms if you're doing manual heat detection. So we developed an automated heat detection system that basically monitors the cows, looks for an indication of heat, and we can automatically draft them and present them before mating. We've developed We've been herd testing for over 100 years. Herd testing is a challenging job, but it's also a job that you don't do very often because it is so challenging. So you have information streams that are sort of 3 and 4 times a year, but the problems that we're trying to address with herd testing are very complex, particularly around animal health, and really what you want is more frequent information. So we have inline sensor technology now that produces somatic cell count information, fat and protein information, and presents it on a daily basis to farmers so that they can make better decisions every day. We have invested in addressing the issue of, I guess, incomplete data. So in any business, any sector, there's challenges with getting all the right information together. So we have information platforms both in the shed, in the office, and physical alerts in the shed that help sort of take that incomplete data and turn it into sort of a meaningful decision. And as farmers have become sort of more tech savvy and networks, cellular networks, etc., have moved out on farm, we've made sure that all of our new technologies are sort of BYOD compatible, so your device, not our device, but also cloud-based, so you can take that information with you, you can gather information on the fly. So big focus on that. And the last piece of the puzzle, which is actually the first thing we did, was develop a drafting system to automate the quite physical challenge of managing animals in the shed and getting them into the right place for treatments, etc. So that's what our sort of technology suite kind of looks like today. We're still advancing and we've got new technologies coming. The focus for all of this has largely been, as Simon's pointed out, about increasing productivity on farm. And I guess I'll lay down the challenge that the future challenges that farmers will face are going to be much more complex and harder to understand and control than they have been. There's a number of factors sort of emanating from these organisations and others that are important challenges for all of us, as humans, let alone as farmers. But it's going to require a hell of a lot more innovation to help sort of achieve some of these goals. And I'm talking about moving from productivity improvements through innovation to efficiency improvements, removing waste. My goal would be to have farmers as profitable as they are today, or perhaps maybe 4 years ago, but with a lower footprint effectively. So what can you do with that land to reduce the overall impact, but maintain a lifestyle and a living that you need to want to go through the effort of farming. So that's what I'd say is the challenge for the future, and that's where we're heading.
There we go. Look, first I wanted to show you a photo I took just a few months ago. Waikato River at Hooker Falls, drove down the river a little bit, and that's at, wherever it is, Arapuni. Probably the same water by the time I get there. That water I'd drink, that water I'd worry about swimming in. Now, you can deny it, you can do what you like, but the reality is this is a serious productivity problem because of the implications of what is being done right now out there. So this is Horowhenua. 400 farms are in sensitive catchment. If they are forced to meet the current requirements, which they should be meeting according to the plan that there's all the fight with forest and bird, 65% of them will go out of business. If you expand that out to New Zealand, that's probably 2,000 or 3,000 farms at risk. That's enough to bring down Fonterra and our banking system. I mean, it really is an issue that people are really a bit ostrachy about at the moment. But don't worry, because we have a solution. The next thing is nitrous oxide. It is a big issue for the government. And it's the one that really is quite serious. Like methane drops out of the atmosphere relatively quickly. Out of 100 years, nitrous oxide is still pretty potent. It comes from urine patches, so what are you going to do about it? Well, we've got a solution for that too. So the problem of all of these things, this sort of big looming environmental thing that everyone's trying to pretend isn't going to happen, but some people are really trying to do something about, is the urine patch. That's where you see on the paddock the grass grows more vigorously. And it grows more vigorously because there's 20 to 30 to maybe 50 times as much urea on that urine patch as a sensible farmer would be putting on that paddock to grow more grass. That urea is good stuff because it makes grass grow, but it's really bad stuff because there's too much of it and you're losing that fertiliser off the farming system and into the environment in various ways. Now we have this big machine we call Spikey. One day it'll be on a robot and it'll be smaller, but for the moment it sits on a 3-point linkage of the tractor, and it actually is used in a follow the cows basis. So the cows come out of the paddock, you drive it over the paddock, it detects your urine patches and it treats the grass only on the urine patches. And that's quite important because if you want to do something to reduce the availability of nitrogen on a non-urine patch, then you're going to hurt your growth and the whole thing's going to go backwards and the farm's going to make less money, not more money, which really isn't the objective. So Spikey's used follow the cows basis. It also has a FERT spreader which is very accurate, which has other advantages. And Spikey itself is very good. This is independent research done by Manaki Whenua, Landcare Research. There's a little bit of GPS registration error because I used a cheap GPS, but the thermal is where the urine patches were actually placed, done with a thermal camera. And then all the other lines are what Spikey detected out to 2 days. So we can accurately detect urine patches out to 2 days. In fact, we can accurately detect them out a lot longer than that unless you get very heavy rainfall. But 2 days gives you a working frame in which you can do something practical. No point in coming along and saying, oh, lots of grass is growing here, let's treat it, because it's too late. You can't do anything about it. So what happens is a cow pees, and in the pee there's a whole lot of urea. The urea relatively quickly binds to ammonium and becomes insoluble. Then it turns to nitrate, which is water soluble, so the plants can use it, and that's good because it grows more grass, but it's also bad because there's so much of it. It's like a colander. Every urine patch, if it rains, you're going to lose nitrate due to it leaching. So we spent probably more on what's happening here. And if you ever get into a business, by the way, get something electronic, mechanical, or chemistry, but don't add animals in and do all three at the same time, because it's a bloody nightmare. But anyway, having said that, what we do is we make it stay in that ammonium phase for a lot longer with a nitrification inhibitor, which is one that we've developed. It's definitely not DCD. We also, that's part of the trick, but the next part of the trick is to actually denitrify more of that nitrate by providing carbon for the bacteria so that they can actually do their stuff. And the good thing about that is when the bacteria die, you can get a bit more nitrate back later on. And then finally, we put a growth promotant in there as well to make the grass grow even more vigorously. So the outcome of all this is cool because the farmer is keeping his fertiliser in the farm, growing more grass. So he's actually putting his productivity up. So these are real numbers off a Rotorua farm, and he's growing over paddock-wide basis about 15% more grass. Of course, the leakier your farm is, the more we can do for you. And there are situations where we just can't grow more grass. For example, midsummer in Canterbury, on one farm, they were growing 6,000 kilograms of dry matter in 2 weeks. I'm sorry, but physically grass can't grow any quicker. But then at that period of time, you're not getting rainfall, you're not getting leaching, and come into spring and autumn, then we can have a really big impact. So it is all about productivity. And our real goal as a company, apart from funding our founders who desperately need some funds, is to actually get people to use this technology because they want to, because they make more money. If they're only going to use it when they're forced to, then it won't have anywhere near the impact that it could have on the environment as if they use it if they want to. I mean, if every farmer uses this and the sorts of results that we're getting out of our research facilities are replicated, we will reduce New Zealand's global warming footprint by 10%. I mean, it's huge. It's the biggest single thing anyone can do. And that's sort of the next point I want to make, is we got some really amazing results, which I'll tell you in a little bit, at Christmas, but we needed to verify them. So we've really invested heavily in lysimeter facilities. What these are is they're big tubes of undisturbed dirt, which have a bucket that they're placed in, and then a drainage from the bottom, and then you repack around it. It's incredibly hard to make, particularly in Canterbury, because you've got all these stones that want to drop out and you can't disturb it. So it's basically like an archaeologist. You're brushing all the way down as these things are going down, and you're spending hundreds of thousands of dollars, but it is really one of the few ways you can actually measure what effect your treatments are having. So this is one facility we've got in Palmerston North. This is another one being constructed, that's in the construction phase, in Canterbury. And the results that we're talking about that really are game-changing, we're looking at 70% decreases in nitrate leaching. The Christmas results we got were 74%. And right at the moment, I'm just desperate to get the results from the leachate we collected and all the rain we had 2 weeks ago. Because if we can repeat those results in this bigger facility, then we really have actually, we've solved the problem. I mean, we have a solution which grows more grass. What more could you want? Less science has gone into the nitrous oxide, although there's actually a really big NZARGC, New Zealand Agricultural Greenhouse Gas Research Centre project on at the moment, looking at various treatments and the impacts they can have on nitrous oxide. And then, of course, there's the extra herbage growth. That's the extra grass that you're getting. That number there is taken from lysimeters. Because of edge effects, you actually get more when you put it out in the paddock. So we feel it's pretty cool, exciting stuff. This is where we are now. Typical farmer, typical tractor, not quite so typical bit of machinery on the back. That particular one has been running for 2 years on 4 farms. So it's in pretty much solid continuous use, and certainly been a learning experience, but we're really confident now. We have another one in Wairaki as well. one day we want to tow it with a robot. It'll be a much smaller unit because the robot's got all day, and that's certainly something that we've been looking at. We've even built the robot you see there. It works and it sort of does the job, so we're 10% of the way there on making a real product. There's a lot of development required if we were to use our own. We may well talk to somebody like Robotics Plus and see what they've got. And then, of course, the actual treatment. We're at the Model T Ford end of the spectrum. We've got something that sort of works, but imagine once we start taking into account the weather forecast, the soil moisture, the time of year and so forth, and really playing with the ingredients. There's already 3 or 4 ingredients in there, and some farms need a bit more sulphur, a bit more this or a bit more that. So one day that'll all be web linked as well, and the gains start to be huge. You can use a lot less fertiliser and grow more grass. Well, what more could you want? And that's really the story that's behind pastoral robotics. Thank you.
So yeah, I'm Henry Williams. I'm a research fellow up at the University of Auckland, the CARES group, working in the robotics, and particularly on the agricultural robotics projects we're doing. Basically just here today to talk about one of the new projects that we've got going. Basically, as most people know, in orchards we've got a massive labour issue, not only in the amount of people we can actually get in to do the work, but the quality and consistency of that labour that's actually, of the work that's actually being done. So effectively what we're doing is we're looking at systems that can go through your orchard, they can extract metrics about your orchard, the individual trees, all the things you want to know about your orchard, so that you can then use that information to make better decisions about how you actually manage it. And then that's one part of it. The next part is actually enacting those decisions. It's one thing to know what you should be doing. It's another thing getting the labour to do it and then to get them to do it correctly. So what we're doing in the Human Assist project is, first step is developing systems that can, one, improve the workers, make the job a bit easier for the workers to actually go through and make these decisions. So if we take grapevines, which we're working on at the moment, is making better decisions about what to prune when you go to prune the grapevines. So at the moment, basically have to make a series of calls about which ones to cut off, which ones to leave on. If you make the wrong decision, you can basically destroy your crop. The whole vine will die, or it just won't be productive for the next few years. Making those decisions in orchard and making those cuts is quite hard. Training someone to do that and getting them to do it consistently is tricky. So what we're trying to do is develop technologies that are able to actually tell them what to cut, where to cut. So basically all they have to do is then go and do it. The second phase is then full automation. If we can tell a person where to do it, once we get it accurate enough, we'll get machines to do it. So part of that's basically collecting all that data. So at the moment, a lot of these decisions are made quite simply. They can't use information that they want to use because it's just too much to teach someone to do. With our systems, we'd be able to go through, measure the length and size of the orchard, measure the each individual tree, and do exactly what that individual tree needs to do, not a generalised approach from 1 or 2 counted trees across the whole orchard. Using a whole range of sensors, from cameras to LiDARs to thermal imaging. And then, human assist. So basically, the other one is apple fruitlet thinning. So at the moment, they're given a set of very simple rules that they have to go through and apply. It's very, very simplistic. What they'd rather do is go through and say, we want you to apply this specific rule to this specific tree, because this tree has a certain tree thickness. It's got a certain number of branches. It's got this much foliage. So for this tree, we don't want you to do the standard. We want you to do this very specific set. Trying to explain that to someone for each individual tree gets quite tricky. So we're trying to develop systems that can do that. You can actually apply it at an individual tree level and then basically just tell the person, thin these particular apples is the idea. And then ultimately replacing the person with a robotic system. So developing basically yield estimation, tools to also train people how to do this. So running them through scenarios where this is what you should do for each individual tree. And then, of course, through all this, by being able to actually make better decisions in the orchard and individually select particular fruit that you want to think, you can improve the quality of the actual individual fruit. So with selective fruit harvesting on blueberries, selective fruit thinning on your apples, and pruning on your grapevines, if you make better decisions, overall, long term, it improves the quality of your orchard, improves the quality of your output. And of course, we don't do this alone. The current Agritech project, or the Human Assist project, as we call it publicly, I think. It's a team of different other universities, University of Waikato, Mike's here as well. Got a whole bunch of, got a lot of industry involvement, a lot of the orchard owners, Villa Maria, etc., all telling us what they want, how they want it. So we spend a lot of time in the orchards. Probably talk about the Kiwifruit Orchard project at some point, but we actually spend a lot of time in the orchards running, testing this technology. We don't just do it in the lab. For the last project, I spent pretty much half my life in a kiwifruit orchard testing these systems in commercial orchards, making sure it actually did what you said it did, instead of just in the lab. And then, yeah, lots of industry partnerships. So basically everything we do, we go back to them and say, is this what you wanted? Do you want more information? What do you want us telling you? How accurate does it need to be? Have we met your standards? Or have we just accidentally destroyed your tree? Which we did once or twice, unintentionally.
My name is Burhan, work in Callaghan Innovation. We are part of the Robotic and Automation Group. That is a subset of the research and technical services in Callaghan. So basically what we are offering is servicing in science by bringing basically the results from the universities, research centers and whatnot, building technology, prototyping it, and helping industries into get into that next stage in which they want to be, if they want to be competitive, especially when it comes to exportation. So a few facts that probably all of you are aware of. There is a plan that horticultural goal is $10 billion in 2020. We are on the right track because we are at 9.2 this year. These are the fresh statistics. This is very good when you think about that. Probably about 2/3, if not more, of these are producers relating to kiwi fruit, grape, but it's not limitative to that. But that gives you an idea about the amount of money that is involved in both making this industry and the revenues from it. Yet we have two aspects. One that I don't mention here in my slide, which is basically the shortage of expert manpower. And I was told by an expert some time ago that if you don't find the right number of workers that are specialized in something specific on a seasonal operation, the produce of the year might be decreased by 5%. That's a lot of money. The other one that is obvious to every agriculture is basically the climate change and the pests and or different kind of diseases that can basically plague the produce. And different kind of producers will suffer different kind of amounts of reductions and losses, such as, for instance, for the kiwi fruit, $885 million of loss. That is 30% of the production. No thanks to PSA is really a bad thing. So I'm not here to advocate robotics or artificial intelligence for that matter. They are just a mean, but they come actually as a good help into mitigating the losses and helping solving both the problems. One of them being basically helping to lift up the responsibilities of the workers into doing more interesting jobs and not basically replacing them. And the other thing is to help with the machine smarts to do all the pre-processing that helps the man or the woman for that matter to make the right decisions when they have to do the exercise of their agricultural production for that matter. So robotics enter into this kind of activities in order to basically solve a lot of things. What we are trying to do with these robotic systems is to get them smart enough to leave a little bit the automated and redundant job and help to do part of the job in which the human and the machine are contributing in some interactive manner, a good manner. And that means that the machine has to rise to that level itself to be capable of collaborating without hurting the produce, the man, or the environment. For that, we can think of many things that you could use a machine for, and machine being either a computer that is going to collect software through software data and basically post-process it, such as we are doing right now quite well with data analytics for farming or for that matter any other aspect of statistics, or otherwise basically go in and do a part of the work of the farmer that would wake up at 5 o'clock in the morning, go walk in his field, and look at his trees or at his produce. Now, if there are 3,500 trees, probably it's become a little bit of a bad thing to do, and it takes all the day. And I'm sure no one has time for doing just that. So the idea is that a robotic system that is mobile enough, that is communicative enough, that has all the means to be capable of doing a specific job and replace by that the redundancy of the work for the human is a good thing, not a bad one. Then you can do basically horticultural management, you could do yield estimation. Basically the machine can go on and check for your produce and for your investment for you, while you are probably sitting somewhere in the porch of your farm sipping some iced tea, but looking still at your screen, I guess. So one of the activities I am basically dealing with is a little bit, the applications you can see are basically, sky is the limit. It's up to you basically to come with your super ideas, what you want actually to be doing, and basically we could sit around the table and shape it and bring it to a certain degree of reality using both the research results, the engineering, and the people that are outside that also own businesses with which we and you can partner. So it's not just about we doing the job for you. If we know somebody that has the solution to your problem, we will be more than glad to guide you to them or to get you to match. So one of the activities that I have been dedicating my year for is to detect diseases in trees. So the idea that scenario is simple. Basically, you get a machine doted with a certain amount of sensors and go and visit basically a line of wine trees, say, and basically look and scrutinate, not just scan, but look and scrutinate. That's what I meant by raising the machine to the level in which you can have it to do certain things that we, human, would do, which means biologically inspired systems. So we are going to look at things generally on a landscape, but your eye will be naturally attracted by something specific on a tree or at a specific detail that might, after a specific diagnostic, be giving you some result about something that you don't wish to have in your vineyard or in your horticultural environment. So the idea is that you have data happening, something very classical, but you are doing it dynamically. You are not waiting that you collect data on a year and do something about it on an analytical base. You have a system that is capable of looking at things, perceiving the environment that, rather than observing it only, and basically doing some cogitation behind and giving you some information about what's going on in your field and possibly tell you, go and do something about it. So that's basically the level of the intelligence we can reach for so far. So the idea would be actually to look at certain environment, to detect the objects of interest, to detect other objects that might be there, a worker, a bag of fruits, you name it, a tractor or a vehicle, and basically based on this information begin to follow a specific trajectory which make your machine more or less autonomous, at least capable of planning properly. While you are detecting the object of interest and you are following them, you would stop probably at every one and decompose that into the pieces that are of interest to you enough to motivate a camera system or a sensor of that sort to be capable of looking up and down and left and in the corners to detect if there is anything wrong with your tree. And basically, because they are tagged and you have some specificity about their characteristic, you can follow them basically and have a generation of a real-time database that is telling you tree 136 has something. And so forth. So basically, you can come later on with an engine that is doing some specific job and telling you what is the extent of the damage you might have. Another thing that you could do that is even better is that if you do this around the year, you get the full statistics because you are following the growth of your fruits or because you want to detect at the earliest stage what you are basically trying to avoid. And basically a parasitical thing or the presence suddenly of a new insect that you don't wish to have on the leaf of your trees and so on and so forth. So basically that's the idea. A simple operation here, your priorities, your projects, your ideas. If you contribute with us on trying to find a solution, we'll be more than glad to bring and help you to come to your success. Please come and talk to us. Thank you very much.
Thanks, Simon. I'd like to start just to really to acknowledge and thank all of our partners. Without their help, we wouldn't be able to do what we're doing today. If I think about our commercial partners, we've had Yamaha have invested $10 million into Robotics Plus last year, so great help from them and a great strategic investment. We have organizations like ISO, like Global Pack Technologies, which is a joint venture between Jenkins Fresh Pack here in New Zealand and Van Doren Sales in North America. They're our distribution partners for some of our technology, and other organizations like Trimex. So we really appreciate those commercial relationships. We also really appreciate our relationships with the academic institutions. So Waikato University, Mike, good to see you here. Auckland University, good partners of ours. The regional research institutes, plant and food technology. We work with all of those guys who are really bringing the technology, the research through that allows us to be able to commercialize that. And finally, just like to thank the governmental partners that we have as well. They often get a bit of stick, but we like to wave the flag for Callaghan Innovation and the likes of NZTE, because without their help and support, we simply wouldn't be able to do what we do today. We wouldn't take some of the risks that we take, and we certainly wouldn't be able to move as quickly as we do. So a big thank you to Callaghan Innovation. So there are my thank yous out the way to start with. What I'd like to do is just talk to you about three technologies, the three key technology areas that we're commercializing. The first one is around fruit packing and apple packing. The second one is around log scaling. And the third one, which is more in development, we haven't actually commercialized them yet, but they're coming pretty soon, are the unmanned ground vehicles. So this picture that you can see on here is 10 of our apple packing machines in a packing shed in Yakima in Washington State. We're actually going over there on Sunday to see these machines and work with Yamaha and our distribution partners to think about the future and the next generation of machines that we're designing. So this is a classic North American pack house. Just about everything before this stage and after this stage is highly automated. But you can see here there's still a lot of people just picking and placing apples and orientating them into display trays. So we've designed these robotic apple packers. They have robotic vision inside them so they can see the apples. We use neural networks and artificial intelligence so we can detect the calyx and the stem of the apple. We can detect which side is coloured or blush in the apple. And we can basically rotate them and orientate them and then pick them up with these 4 masts here and put them into display trays. These machines are packing at around about 120 pieces of fruit a minute. And depending on how many of these you install, you can get increasing benefits from your human resources. So I think that's that one. So the next commercial product that we have is for log scaling. This is actually a picture of Tauranga Port. If you've ever driven past there, you'll see this massive wall of wood that sits on the port side. Let's see what my next picture is. Until very recently, I should say that when they export and import logs, the unit of measure is volume. So you have to know the volume of it, not the weight, okay? Because in fact, logs can gain 15% of weight in the winter when they get waterlogged. In the summer, they can sit on the port side and lose 20 to 30% of their weight just through evaporation. So weight's not a great measure when you're trading wood, so it's done by volume. And until recently, unbelievably, all of those pieces of wood on the port were measured by human beings with rulers. This is actually a really dangerous environment. More people die from falls from this height, from around about 1 metre, than they do from above 2 metres. Because you've got no chance of righting yourself. If you fall from here, you're going to hit your head first, and it's quite serious. They did put in some gantries between the logging truck and the trailer. The drivers have been known to drive out with those gantries still in the down position. So it's a pretty hairy environment. So what we did is we designed a 25 metre long by 5 metre high by 5 metre wide robot. And if you go to the University of Waikato stand, you will see the camera bar here is on display. And effectively, we just run over the packets of wood, gathering data, both two-dimensional photographs and LiDAR information. So you can see it here taking pictures. We can scan 3 trucks in the time that it takes to manually scan a truck. So it's a lot quicker. We have gamers who work for us and recreate 3-dimensional rendered images of logging trucks. So previously, an exporter and an importer would just have like an Excel spreadsheet with the numbers in there. Now they can actually physically see the log that they are exporting or importing. So there's a really great audit trail that we've got now. You can see here that with neural networking and artificial intelligence, we can teach the computers to find the outside edge of the logs, multiply that by the length, and effectively then working out the volume. So that's also commercial. We launched that in Tauranga with Minister Parker came and cut the ribbon last Thursday. We've got 2 in Tauranga. They've now completely stopped doing manual scaling. They used to have 4 lanes manually scaling trucks. We've now got 2 autonomous lanes that are doing the whole lot in Tauranga. And we've got a plan now to install these in Napier at the moment, we've installed the first one, 2 going in there. They're going into Gisborne, Marsden Point, and then we're going to try and roll them out across the country. And then, of course, there are international opportunities, which is going to be the next stage. And the final technology that I want to talk about is around orchard robotics, or unmanned ground vehicles. That's a picture of our multi-purpose vehicle. We're actually developing a number of these. Some of them are multi-purpose, where you put different applications on the same robot. Others will be a robot that's basically just for a single application. So this is a little video of that autonomous vehicle driving through the orchards that Henry will know very well. He's spent a bit of time here. This is just outside our facility in Tapuna in Tauranga. What you can see with this one is we've got vision systems that are looking up, identifying the flowers, and then spitting pollen directly into those flowers. So this is a technology with a world without bees. You can see the flowers sort of moving as we're driving under them. This technology uses about half the amount of pollen that you would use in traditional methods, and bearing in mind that pollen costs about $5,000 or $6,000 a kilo, it's quite a saving. Yeah, so there we go. This one travels at about 4 or 5 kilometers an hour when it's doing this particular process. Many of you will have seen this technology as well. This is a little bit further back in development. It looks quite sexy, but it's not quite commercial yet. What we're doing here, obviously, is harvesting kiwi fruit. Again, there are vision systems that can identify the fruit. There's a lot of technology also just in that movement of the hand and the materials that you use to grab the fruit so that you're not damaging it. Yeah, a bit more of the same. Oh. Okay, here we go. And this is another piece of technology that we've been developing again with the universities. This is looking at yield estimation. There's a real issue in growing systems that both the farmers and the sellers don't know how much produce they're actually growing. It can be a real issue for the likes of Zespri, who are forward selling, forward shipping. It's a problem for the pack houses who have to buy cardboard before the season. It's a problem for Jenkins Fresh Pack, who have to produce labels that go onto the fruit. So knowing how much fruit you're actually going to produce is a big deal. So what we've done is we've developed technology that we can drive under the canopy, again with cameras and LiDAR. This is about I think it's about a 2 hectare block, about 650,000 fruit. The colours, each dot on this video is a kiwi fruit. The colour tells you how far from the ground it is. So if it's red, it means it's below 1.5 metres and is likely to get damaged if you put any kind of mechanical tractor through the orchard. So you can see we can plummet through the canopy here. And those that are purple are going to be above 2 metres, so are highly unlikely that anybody's going to be able to actually pick them. So this kind of technology we're hoping is going to really help both the grower understand when they're going to be able to bring harvesters in to pick the fruit, but also everybody else in the value chain right through to the final customer. You can see some big black patches there. That's actually where the male trees are. Obviously, it's a dioecious plant, is kiwi fruit, so they don't obviously bear fruit. But it also will help the orchard managers find where they've got problems in the canopy. So also it will help the farmers. And that's the part of the team. We were finalist 6 times over in the New Zealand High Tech Awards a couple of weeks ago, and we came away with 2 gongs. One of them for the apple packer that I showed you earlier on. So thanks very much.